Hello, welcome back. Welcome to part 3 of the lambda calculus lecture that I'm giving. Hopefully you saw part 1 and 2 before. Part 2 is uploading right now, but by the time you see this video it's probably uploaded. So, alright, let's get right into it. We were in the middle of doing these 11 questions, and now we're on this last one. Can you simulate a Turing machine using lambda calculus? You should probably look up all about Turing machines and stuff. Yeah, there's a lot of history. Hopefully you know a little bit. It's nice to know. Alonzo Church, the guy who invented lambda calculus, had a student named Alan Turing who invented the Turing machine, and they're pretty much equivalent in power, but they're two different things, kind of. Like Turing machine is like reading and writing. Lambda calculus is expressions that simplify. That's pretty much what you can watch this video probably. Turing Machines Explained. You have this head reading on a tape, and you could flip it 1 or 0. It has some state instructions and stuff, and yeah, that's what Turing Machine is. So in order to do it in lambda calculus, I'm going to go ahead and implement the simplest Turing machine that I know of. It would be this one, this small fudge interpreter. It's really simple, right? So it gets a list of ones and zeros, which is the tape, and then a list of commands, which are these symbols: left, right, flip the bit, jump to the matching bracket, and then jump back to the matching bracket, right? Jump past the matching bracket if the current value is 0, and then jump back to the matching bracket if the current value is non-zero. Alright, so here's one thing about this that is a little bit unfortunate, and it's that this interpreter is not like extremely efficient. I kind of made it myself. I'm not like the best coder ever or anything. There's probably so many ways to make it more efficient. So it's gonna be kind of limited a little bit when we test it. So just to make really sure that the code is correct and that why I say it's hard is why it's going to be hard to test is because it's going to be really inefficient. We're not going to be able to test that much with it. We're going to be able to test a little bit. And so the reason, that is the reason why I implemented it in Haskell as well. Pretty much kind of like a copy of how I did in lambda calculus. And I did it just so that I could be sure that the code is correct. So if you want, after you do it in lambda calculus, you might want to look up a little bit of how Haskell works, and then you could implement it in Haskell because they're pretty similar. At least anything you can do in lambda calculus, you should be able to do in Haskell. So anyways, let's just start implementing it. We want to talk about what this thing takes as inputs, right? Here would be a good place to look at it. Here it shows us, right? Interpreter star, and then 00101100 should be 1010110. How does that happen? Real simple, right? So you probably should read all of this in case I don't explain everything, because I don't want to take forever in this video. But yeah, your pointer, your pointer starts at the first place, right? At 0, would be the first element in this list, which would be right here, right? And then we can move the pointer left and right with these commands, the left and right commands, right? And well, anyways, it starts at 0, so the bit that's at 0 would be this very first 0, right? So if we flip that, we would flip it from 0 to 1, turning it into 1, and so that's why this is the result right here, right? 0 0 1 0 1 1 0 0 would turn into 1 0 1 0 1 1 0 0, right? Just that 1 is different. And this one would move the pointer to the right, flip, move the pointer to the right, flip. So these two, the 0 and the 1, turns into 1 0 in the other tape. And then the matching brackets is not tested in the sample test, but you should know what they do, right? It goes to the matching bracket. So let's say I had some random thing here with brackets. What's the matching bracket for this one? Well, it's this one. What's the matching bracket for this outer one? It's that one. That should make total sense too. So let's start implementing this thing. Well, the thing about these symbols is that, well, why don't I just have numbers to represent them? That's just what I'll do, right? So, I mean, real simple. I can just have natural numbers to represent them, and then these will be, and then my code will be a list of natural numbers, which should be easy enough to deal with. So, that's 2, and then 3. Notice that I'm putting them in these little quotations because I already have functions for greater than and less than and multiplication, so I'm gonna have to name them something else so I don't conflict with those. Alright, and this is 5. It's pretty straightforward and simple. Alright, I guess what I'll do is start implementing the main skeleton of the function. It's going to be recursive for sure, 100% recursive, because, well, we're going to do a lot of stuff in it. You'll see. Okay, so interpreter. And it takes a code as input and a tape, and we're going to pass it to the Y Combinator, interpreter, recursive version, code. Alright. Alright, so just so you know, the way that these instructions get interpreted is from left to right, obviously, right? So first it moves to the right, then we flip the bit, then we move to the right, then we flip the bit, right? We go in order. So we would start with our index being 0, right? Index of the what's it called? Index of the index in the code, okay? And then the tape, and then the pointer at which the tape is, right? Alright, here's the thing though. I know I'm just going to make it an integer because it can be negative. You'll see. It'll make sense. If you want, make the index integer if you want as well. You know, if that'll make it easier for you to do it, but I'm not. I know it can be a natural number, so I'm going to leave it as a natural number. And now we'll write the actual interpreter function. Alright. First parameter is always a recursive call itself, and then I'll just put in everything else that's there, the index and the tape and the pointer. Okay, and then a dot. And then first we'll check the base case. Basically, we'll check if the recursion is ended. And the recursion ends if either of these things is true. Either the index is greater than or equal to the length of the code, or either that's true, or two things. Either the pointer is less than 0. Ooh, I should make that function for integers. Less than 0. Or the pointer, or the absolute value of the pointer. The absolute value of the pointer is greater than or equal to the length of the tape. Alrighty then. So that looks like it works. Alright, just real quick. We'll want to do less than 0 function for integers, and also greater than or equal to 0 function. Why not? And it's not just gonna check the sign. It should do a little bit more, because actually -0 is not less than or equal to 0. So that's pretty much the edge case that I'm thinking of. So anyways, it's gonna take an integer and return a boolean, right? So that'll be this one, less than 0, and it takes a integer number, and for it to be less than 0, the sign has to be negative, signum n, not signum n, right? We want the sign to be negative, and the absolute value to be greater than 0. Yeah, greater than 0. Yeah, abs n greater than 0. So that's the less than 0 function. How about greater than or equal to 0 function? So it takes the n, and we just want to make sure that either of these things is true. Either the absolute value is 0, right? Abs n, right? Absolute value is 0, or the sign is positive. That's pretty much it. We could check that real quick. Less than 0, -0. Oh, that one, and then 0. Is 1 less than 0? Of course it is. And we can ask greater than or equal to 0. So -0 past that. Yeah, this 0, 1. Okay, good. Okay. So we could ask all this stuff, right? Is it true that we have ended the recursion? If that's true, then we just return the tape. And you'll see the tape will be the correct one because of recursion, you'll see. So now we want to ask a bunch of other things, and just yeah, whatever is between these two parentheses is what will happen if we don't end the recursion, which is some stuff. Now, I know I'm going to write these two values more than once, so I'm going to just have them here just to make things less writing for me. And that V will be element, whatever element, it's going to either be a 0 or 1, abs pointer, tape. And so now I'm pretty sure I'm going to have to define that function, element at, right? So how do I get the element at a certain index? Well, it's going to be under here. It's going to be in the functions that give you a list, that take a list and give you an element. All right. This would be lm at n from the list. Here's how I actually have to do it. I actually have to drop a couple values from the list first, and then get the head of the list. Right, so first drop a couple values from the list, and then I get the head of the list. Simple. That's element at. Except that now I don't think drop has been implemented, so I'm going to have to do that. Drop equals, yeah, it takes a list. Well, actually it takes a number and a list, and it drops that many numbers from the front of the list. So that what I'll do, real simple. I just have to apply tail to the list n times, right? Yeah, n times the tail of the list. That'll drop it, and let's find out. All right, so where's my list? A, B, C, D. Now let's drop 2 from the front of the list when we should end up with C, D. And all right, so let's do that. Drop 2 A, B, C, D. All right, expression contains dot but not lambda. 2, 2, 2. Okay, here it is. I didn't write a lambda symbol, so it should be lambda and list dot. Okay. Drop 2 A, B, C, D. We get just C, D. How nice. How about drop 0? Right, we should just get the same list back. Drop all 4. We should get null. Okay, cool. So that works. How about just getting the elements at at 0, 1, 2, 3, and that works. And just for fun, we're gonna get it at 4, which doesn't exist, but let's just see what it is. Look at that, the underscore and then a true after it. Yeah, so pretty much no element at 4, and it's just nonsense. So okay, we have element at abs pointer tape, and here we want to use it again, I guess, actually. And here's this is going to be what f is, and so it's actually going to be equals to x, right? Does it equal to x? Does what equal to x? Elements at the index in the code. Okay. And now that we have that, we can actually start doing a bunch of checks, right? So we could check, is the current element and the index of the code that one, right? The right. Is it currently going to the right? And so now it actually makes sense that I made these integer natural numbers, because I've defined a quality for natural numbers. So that's nice, right? So I could ask for all of these things, right? I could ask for, is it to the left? Is it to the right? 1, 2, 3. Do I flip it? Do I go there? Do I go there? Alright, well, one at a time, right? If it's the case that we go to the right, we're going to recurse, right? We're going to go right back into this interpreter function, and pretty much all the values are going to be the same. So the code is going to be the same, except the index is going to go up by 1, right? Because we're going to, after this, we're going to consider the next instruction, right? We're no longer going to consider that going to the right instruction. We're going to consider the next one. So that's why the index will go up by 1. And then the tape stays the same, and then I also add 1 to the pointer, and it's an integer, so we could use our integer add 1 to the pointer, and that's pretty much it. We recursed, right? And if it's not the case that this is true, if this is not true, then we don't go here, but instead we're gonna go on and gonna go in between these parentheses. Yeah, so everything in between here is gonna be what happens. It's pretty much going to continue to the next line down. Even though functional programming is about evaluating expressions, I can kind of write it in a way that makes it seem like we're executing a bunch of instructions, right? We're checking from top to bottom. Alright, so now pretty much what happens here is we recurse, and instead of adding 1 to the pointer, we subtract 1 from the pointer. In this case, in the next case, what we would do when we recurse is have all those the same, plus 1 to index, and instead of the tape, now this flips the tape at the pointer. So I'm going to be real specific with what I call this function. New tape with bit flipped tape, and it flips it at the pointer. And the pointer stays the same. We don't change the pointer in that in this case. And I'm going to have to do these little parentheses after. It's like, yeah. It's one big expression, don't forget that. Alrighty then. Here we have the code, and we have, actually, it's not enough for it to be an open bracket. It has to be an open bracket and the value at the current cell has to be 0. And same for the next one. It's not enough for it to just be a closing bracket. The value at the current cell has to be non-zero, right? So what I'll do is right here I have the V right there, element at abs pointer tape, right? So I could actually say is okay, so here's the thing. So the tape is going to be not ones and zeros, but true and false, because I think that'll actually be simpler than using ones and zeros and flipping a 1 or a 0. I think flipping a true or false is much easier. I could just say not V, not the value, right? And in this case, I say V. And not only, I mean, I'm also saying, I'm actually saying and these things are true, right? And so same here, and right, so both of those things have to be true. The value at the tape has to be true, and the character has to be an open bracket, and for the case of the closing bracket, it has to be a closing bracket, and the value of the tape has to be sorry, I mixed it up. It has to be true, and then this one, for this one, it has to be false. So like, you know, false 0, true 1, pretty much like that. And I'm just gonna line these up so it looks all nice and neat. And okay. So in this case, the index. Oh, okay. So now here. See, look, this moves us to a different place in the code. So we'd have to find the index of the closing, the corresponding closing bracket. So I'll just put this function right here. Jump past closing bracket, code IDX. And tape can stay the same and the pointer stays the same. And I'm pretty much going to write a very similar looking function here. I'm going to put the brackets here, and this one would be called jump back to the opening bracket. Yeah, and now, alright, we want to just put one more expression in here, right? Because if this is not true, then we still have to do something. And what will happen if none of those things are true? Then either the code is something that should be ignored, or pretty much it was a matching bracket. It was a bracket, but this thing wasn't true, the condition. So pretty much what would happen is we would just go to the next instruction and everything else would stay the same, right? So the only thing that we'd write is +1 IDX. And then everything else is the same, tape, and then the pointer. Yeah. Alright, and I think that's pretty much the skeleton of the interpreter. Pretty much, I think that's pretty much everything we have to write about it. And I have to uncomment this as well. Alright, interpreter equals this stuff. Okay, but now we want to write the other functions. So we'll go ahead and do that. Let's see how we're doing on time. 23 minutes have elapsed. Okay, we're doing okay. First one we can do is probably new tape with bit flipped. That seems like the easiest one to do. So we'll go ahead and do that, right? First I'll go ahead and define some random tape. I don't know, TFTT equals, and it's going to be a list that starts with T, and then the next element is going to be F, and then next element is going to be T, next element is going to be T, and after that is null. Okay, so that's our list, and now we want to define this function, new tape with bit flipped. Yep. And guess what? I already know it's going to be recursive. So why don't I go ahead and do that? It's going to take the tape and a pointer because I already said it takes a tape and a pointer. And we'll just do the y combinator to, I'll just name this one, since it's so long of a function, I'll call it new tape with bit flipped. And put a percent sign, tape p null. Why do I put a null there? Because I'm about to teach you how we could map over a list and create a whole new list with just one thing different. So here we go, right? How do we change one value in a list? The way is by creating a whole entire new list out of it. And that's why we start with null, right? So let me go ahead and start writing this function, new tape with bit flipped, the actual one. New tape with bit flipped equals recursive call tape and then a p, and then instead of null, actually it'll end up being the result. Right? So what we want to do is first check if we're done, right? The base case, right? So we check, is the tape equal to null? If it is, then we just return the result. If not, we're going to do some other stuff. Or actually, we'll recurse, right? We'll go back into the same function, but we'll do things a little bit different, right? Tell tape. So that, right? So now the tape is getting smaller, right? It's getting smaller and smaller, and eventually it will equal to null, which means this eventually will end, right? So, right, we take away one from tape, and then the pointer, right? Well, actually, the pointer, I could subtract 1 from it, right? And now it makes sense. It makes sense. You'll see why it makes sense that it is integer and not a natural number, is because I want it to go below 0 when I'm doing this. Because, well, if it gets to 0 and it's a natural number, it won't get below 0 because predecessor of 0 is 0. So what I want to do is I want to make a list of stuff, right? And we'll figure out what it's going to be in the end. But the second element of the list, right? The end of the list is the result, right? And so we're adding something to the front of the result. What are we adding to the front of the result? Well, it depends. It depends if something equals 0. What equals 0? Actually, the absolute value of the pointer. Absolute value of the pointer. And if that equals 0, what should we return? What do you think? We'd actually flip the bit, right? So whatever bit is there currently at the front of the list, which would be head tape, whatever it is, we flip it. So not head tape. But if it's not true that it's equal to the head of the pointer, then just head tape. And but I realized I could actually write this a little bit better, shorter, nicer, drier. I've basically written head tape twice, but I don't need to. Basically, the function that I'm gonna apply to head tape is either not or ID, right? ID just gives you the same exact thing back, so it's either not, right, or ID. And this is the function that I'm applying to head tape. Head tape. Well, it's only a little tiny bit shorter, but I still think it's kind of nice. I don't think I need these parentheses around here. So yes, just like this. Right? So equals 0, abs pointer. If this is true, then we choose not. And if it's not true, then we just use ID, which lets it just pass. So that's how we could write that. Now we could test it. So now we could why don't I just flip this false into a true? So I would probably be flipping at 1, right? So new tape with bit flipped, and first I pass in the tape, which would be TFTT, and then I pass in the what's it called? The pointer, right? Which would be 1, which is where I'm flipping. And let's see what we get. Look at that. That doesn't look good, does it? Hmm. Alright, I'm getting a whole huge thing here. I'm not seeing any true. I'm actually. Oh, I see why. I see why. I see why. Okay, of course. So T and F haven't been defined. Of course, I for some reason thought that I had T and F defined as true and false, but no. True and false are defined as the actual words true and false. So what we could do to just make list writing right now a little bit easier is I could just make an alias for it. T equals true, F equals false. Let's see what happens now. Okay, so T is true. Let me just make sure that I wrote it right. T is true, F is false. And let's see. What could be wrong? Now I have to figure it out. TTFT. Alright. How about if I just change this just to only be. How about I just change not to ID so I don't actually flip anything and I see what happens here. Okay, so I still get something horrible here. Why is that? Why do I get something horrible? I mean, maybe the list really looks like that when it's expanded all the way. Let me just see. Let me just really see, right? So I'm going to go ahead and get all this and just write it down here with a comment. Alright. Yeah, let me just see what this looks like. TFTT. I wonder if it could look that bad. No, I don't think they're the same. Here's this, and it is definitely different from the last thing that I just printed. As you can see, one of them is super long, one of them is not super long. So we'll just figure out what the bug is real quick. It's nice that it took so long to get a bug. It's good. It usually takes me less time to have bugs. So let's figure it out. If the tape is null, alright, well obviously if we flip new tape with bit flipped if we do null, then it'll give me null, right? That makes sense. How about I just have a list with just true in it, just one value, true, and it's a list, takes true and null. Okay, so I want to flip the bit at 0 for this one, and it should just give me a list of just false. Oh, whoops, I have to call it something else. Okay. Okay, so, oh, 0. Well, that's the same as false, so I don't see why. Okay, let's just figure it out then. Alright. Could it be that what I had written before? Oh, ID. Well, that it should actually just Does that really append to the front of a list? It looks like it does. Okay, so here's the thing, guys. I kind of went in, I kind of started doing this, and just knowing that it leads to the wrong result, but I thought I would see something different. That's the thing. It could be I just wrote it wrong. So okay, here's the thing, real quick. I was gonna make you figure it out for yourself, but we're gonna have to reverse the list while we're doing that. because this kind of reverses the list. I'll show you. Let me just change this to be reverse. Yeah, I'll just copy this and change one thing about it so that it reverses a list. I'll just go ahead and write reverse. I don't want to have to change stuff too much. Equals, it takes a list and it returns y reverse %, list, because reverse will be recursive. So here it is. So we actually want to pass in a null, just like we did with the other function, right? Pass in a null to it, right? Result, and equals null. If the list equals null, then we return the result. If not, we return a recursive call. Recursive call where we get the tail of the list and then we combine the front of the list. So head list, combine the front of the list to the result. Alright, and now let's see it happen. Where's my list of A, B, C, D? I'll just define a list which is DCBA. DC, and I think that will turn into that DCBA. Okay, so that's what we want to do. Reverse ABCD. Oh crap. No. Exit. Yes. Okay, so that does reverse the list quite well. That's good. So now I just want to figure out what is wrong with this function. New tape with bit flipped. Okay. So the first thing is the tape. The second thing is the pointer. The third thing is null. I see exactly what's wrong with it. So this whole time in here, I've been calling the pointer PTR. Maybe you've probably noticed I've called it PTR here, but it should be called P. Okay, now I don't have to just pretend like I never mentioned reverse to you. Just take a look at this. Let's flip the bit. Let's flip the tape. Alright, we get TTTT, right? Which pretty much makes it invisible to us that the list has also been reversed. So we'll just do it to TTTTT, right? And okay, so hard to tell still, but we'll just create that list. So here's F. Here's T. Okay, so now let's see what the result is. FT, and there we go. So look at this. At index 1, this is index 1, right? Because before that is index 0, right? At index 1, we're flipping it to an F. But look what we're getting as the result. We're getting this. So it looks like it's also been flipped backwards. So what we do is we'll just simply use this function that turns a list into another list and it reverses it. And we'll just do it right after we flipped it. So now it should properly flip it. Let's test it out. Flip it at 1, we get TTTT. Flip that one, we get yes. So everything is seeming to make sense right now. All right, we could I guess we can move on to the next one. Yeah, no need to flip it anymore. Maybe flip this one just for fun. False to true. Yep. Cool. So we've got that one down. The next one we want to do is jump past and jump back to. Pretty much once we did that, once we do those two, which probably are maybe the hardest ones, once we do that, I think we're done. We can test it a bit and we can be done with this whole video. It's been 40 minutes. Okay. So, So we want to think about what input, right? Just like this one, it takes a list. It takes a list of booleans, right? It's a boolean list, and it returns yet another boolean list, right? And so now let's think about this next function we want to write. Jump back to. And actually, it doesn't only take a list of booleans. It takes a list of booleans, and it also takes a pointer, which is an int. And there we go. Then it returns a list of booleans. Now jump back. Which one do I do first? Jump past a closing bracket. Right? It's a function. And what did I say it takes? I say it takes a code and an index. Code is a list of natural numbers. So list. I just, instead of list of bool like that, why don't I just do it like this? Bool. Okay, so it takes a list of natural numbers. That's what the code is. And it also takes a natural number, which is the index. And then it turns another natural number, which is going to be what index we are supposed to end up at. Okay, so let's say we have some code right here. The brackets are 4 and 5. Alright, so I could just use 0, 0. Okay, so let me create some code here, and I'll have where we should jump to, right? So jump past opening brackets. Okay, I'll make this 0 and then a bracket and 2 zeros, and then maybe another bracket and then 0 and maybe another set of brackets here with a 0 inside and a 0 around it. And all right, well here we have a pretty big code, I guess. Or I could do it like this, or like, it doesn't have to be too big. If it works for a small example, it'll probably work for the rest of them. Alright, so we have this code, and let me go write it out. It's actually going to be 0 and then open bracket, and then it's going to be a another open bracket, and then it's going to be a closed bracket, and then this is going to be a 0 and a 0 and a close bracket, and then null after that. Alright, cool. So let's think about what's gonna happen here. Pretty much like I can, if I'm gonna jump past a bracket, I mean, I could start at this bracket or I could be at this bracket, right? I guess this one is more interesting because these two, they're right next to each other. So pretty much jump past with this code, jump past with that code, and at index 1 should give me, 0, 1, 2, 3, 4, 5, 6. It should actually give me 7 because I want to jump past it. I guess I could jump to it. It wouldn't be that bad. But jumping past it wouldn't make a difference if you think about it. So yeah, it should give me 7. Right? It should detect that this is the matching bracket, and then just give me one more, the number right after that. And the way we do jump back to the closing bracket function is going to be really similar. So don't worry. Once we do this one, the other one will be easy. So let's go ahead and start writing. And it's going to be recursive because we're going to like iterate through this list. So yeah. And like I said, like I've been saying with the other 2 videos, feel free to pause and try it yourself. I'm going to go ahead and start implementing it. So it takes a code and an index, and then Well, here's the thing though. This is gonna be like jumping backwards, right? I want to go back. I start here and then I'm gonna end up at a lesser number. What I could do, there's obviously like so many ways of doing this. So if you have your own way, please do so. Don't just follow my way blindly. What I'm thinking of is, how about I just count, right? The number of times that I have to go, count the number of steps that I have to do until I reach that bracket, and then I just subtract. That number from the position I start at, and so that will give me the position I end up at, right? So subtract the index that I start off at, right, with, now this is the actual, what I put in here will be equal to the amount of steps I need to make to reach that, right? So it's not like going to be a negative number. It's going to be a natural number, right? So JP for jump past bracket. I'll put that because I always put it. And then here's the interesting part. Here's another interesting part. So this one, okay, so for me to go to the matching bracket, I obviously have to have encountered a bracket first, right? So we want to keep account of how nested we are in the brackets. So we can start off with 1 because, well, it makes... I just realized that I got confused. This whole subtraction thing would actually make sense for jumping back. I just realized this is a total... It's like I'm totally confused to be doing that. So this would be for jumping back too. Then I'll do that subtraction thing. Jumping back. Yeah. Let me work on that out right after. But this one, no, this one's easier because it's just going forward, right? I start at a bracket, at an opening bracket, and I jump past the corresponding closing bracket. So yeah, but what I still want to do is, I guess I want to make the code start at that bracket. That'd be easier, I think. In there, the way I'm doing it, +1 idx, and then so drop from the code, right? And then this will be +1 index. I guess I'm adding it +1 both ways. I'm not gonna do too much explaining. Please just take time to explain it to yourself, or do your own implementation. That could be way better than mine. Alright, so now let's do the actual function, which will be this jump JP closing bracket, parentheses, it takes a R code IDX X, and now how do we know if it's over? Well, if the code is null, right? Equal null code, and or either x equals 0, right? And this tells us that we pretty much have encountered the matching bracket, right? Like we've got there, you know. You'll see, because x will change as we encounter brackets, and every closing bracket we encounter, we'll subtract 1 from x. Every opening bracket we encounter, we add 1 from x, right? So pretty much getting to x to 0 tells us that we've encountered the matching bracket, right? Well, anyway, so if it's true, then we're at the right index, and IDX is the one we return. Okay? If not, then we're going to recurse. And now I'm gonna go ahead and pass in a function that I'm gonna use more than once. I'm gonna use it probably like only twice, but that's enough for me to write it only once, or want to write it only once. And that f will be a function that takes a x and it's return it's like equals x. This stuff, head code, is a head code equal to x. That's what f is. Now after the dot here, we can actually have what we want, which is the recursive call. Recurse, and we make the code smaller by 1, so tail code, and then +1 the index, add 1 to the index, and now this is where we pass in the x, right? What we want to know what x is. Well, it depends. Have we encountered an opening bracket? If we encountered an opening bracket, well, in this case we are jumping past. So if we encounter an opening bracket, we would actually +1, right? Because we're farther away from finding the matching. We're farther away from finding the matching open bracket. So yeah, +1 x. Now, if that's not true, then we go inside these parentheses, and inside these parentheses we can ask about the other bracket, right? And if it's the other bracket, then, well, of course we're going to do -1x, right? And if it's not an opening bracket or a closing bracket, then it's pretty easy to guess. It's just going to be x, right? So that makes sense, right? Hopefully it does. I'm just looking over it real quick just to make sure everything is totally okay and free from bugs. Okay. Looks good enough to me. Yeah. Okay. So well, we'll see. We'll see if everything happens when we test it out. So now we'll go ahead and define the next one, which will be jump back to. Right, it's going to be pretty much defined a very similar way, and I was already in the middle of defining it right here. So so this time since I'm kind of like going backwards in the code and I want to find out how many steps, I pretty much explained kind of my little thought process for this, but because of that I'm going to reverse the code. So reverse, and then I'm gonna have to define this function as well. Take idx code, right? So I'm taking some from the front of the code, and after that this can just be 0, and that can be 1 for the x. Before I start implementing this, why don't I implement take? I just realized there's been no music this whole time. Oh, video pause. Yes. Yeah, we want to keep listening to music. Alright. So take, that's what we want to implement. That's gonna take it's gonna be like drop, right? So drop doesn't actually take a list and give you a list. It takes a number and a list, and then it gives you a list. That's what we do, right? It takes a natural number and a list and gives you a list. That's what drop does, and we're gonna need that for take. Why? Because we actually should use drop right for take. At least the way I'm thinking about it makes sense to me. And so same signature for the function, takes an n and a list, And well, we're gonna have to reverse that function first to drop from the right, and then we drop. Once we reverse it, we drop n. Actually, that reverse I did was reversing last. Reversing inside would be reversing first, right? So we pretty much do two reversals, right? Reverse, reverse. To drop from the right. I think there might be a simpler, more efficient way, but this is the way I'm thinking of it right now. And now that we have that implemented, we could, I could probably test it out with the ABCD. Right? I have a new list right here, which could be AB. Alright, so we're gonna drop right 2 from ABCD and test that out. Drop right, okay. Drop right to ABCD, and it should give me AB. Okay, great. Alright, so let's see. Drop. Okay, right here. Now we can do take. Take is of course gonna take a number and a list, and we're gonna take that many from the list, from the front of the list. Right, so what we could do is we could actually drop right. How much? Well, the length of the list minus the amount we're dropping. So length list minus the amount being dropped, and then we drop from the right that much from the list. Alright, let's see that in action. So now instead of dropping right 2 from ABCD, we're just going to take 2 ABCD. And maybe I'll take 3 from it and see. I just define that real quick. So pretty much we would just get rid of that last element. And that will be ABCD, or just ABC. Take 3 ABCD, and that's just ABC. Great. Alright, so now I guess all my functions are defined so far. Now we can keep writing this back to did I write it in here? Take? I don't know, I thought I did. Okay, so anyways, we want to write this. We're almost done. So of course it's going to be recursive, right? So let's do that. JB for jump back, and we're jumping back to an open parentheses. We're going to put that there, and we're going to put that there. Oh. And it's going to be a function that takes the recursive call and the code and the index and the x, right? That's what the 0 is. It's the index, because I start at index 0 and then the 1, right? Yeah, remember, I'm counting how much it takes me to get to that matching bracket, and then I'm subtracting that from the position I start at. So really, all I want to do is start counting steps, and it can start with 0. So let's go. First, check the recursive base case, right? We check either the code is null or x equals 0, right? We're out of the brackets. Alright, so if that's true, we just return the index. If not, we're going to return a very, very similar function to this. Super similar, actually. So similar. I think the only difference might be, let's see, tail code. Index goes up by 1. The only difference is that now we could just change the plus and the minus sign, right? Because now encountering an open bracket means that you're closer to getting x to 0 and vice versa. Okay. Alright. Let's test this real quick. Jump past. Let's test that this gives us 7. I hope it does. I really think it will. So here goes. Moment of truth. Might just freeze the whole entire program. Let me try again. How's time going? Oh, it's about to be an hour. This should be coming to a close really, really soon. So let's just check that everything works. Too bad about this one. Too bad though, right? It's not working. It seems. It's yet. So let me see what could be wrong here. Everything there looks good. Jump past. It takes a code and an index. Yes. Oh. There could be a lot of things that are wrong here. So this never gave us an answer. Well, then that's a shame. Let me see. What could it be that's not working here? Because doesn't seem like anything should be going on infinitely. It looks good so far. It'd be two brackets facing each other is not good. Of course not. Index keeps going up by 1. Wait a second. Yeah, and the code keeps going down. Tail code equals null code. Let me see. Could be I misspelled something. Oh, whoops. Code is this thing. Alright. Right, of course it's not null. So then what happens? So jump past from here. What happens if I give it 2? So looks like it is totally just like taking. Oh, look at this! This actually evaluated to some garbage. Oh yeah, but how? Okay, there has to be something undefined here that's like it's not being reduced. So maybe just by looking in here, I could find out what it is that's not being reduced. It's like something that I haven't defined, obviously, but I haven't noticed that I haven't had it defined. It's kind of hard to read this a little bit. That's what it has to be. It has to be that. Something has to have not been defined yet, and that I thought I had it defined, but is not defined. So what could that be here? It's not like I have that much here. I'm only using a small part. Let me see. There's just gonna have to be a little bit to look at. I think I don't see it. No. Equals head code. Okay. 0 0. That seems to be all good. List seems to be defined good. I guess I'm just gonna have to rule things out one by one. So let me see. this is the code, which is okay, y, j, p, and then so this is the code, and this is the index, and this is the x. This stuff seems to be okay. Index. I'm a bit confused, yes, because like even if I mean what I don't know what could have gone wrong here except that I misspelled something, and that has to be it. There's one typo. Where could it be? +1. Here's a bracket. Here's that. Here's that. Here's that. Here's that. Here's that. Why don't I just do it on a simpler list? Let's do it on. Let's do it on this list right here. Yeah, that'll be the list. And so let's go ahead and define it. It's going to be a list that takes a bracket. Then it takes, then that's a 0 there, and then that's going to be a closing bracket. And then, oh, after that will be null. Right. Okay. Okay, so I don't want to do it at 1. I would want to do it at 0, and it would give me 0, 1, 2, 3. It should give me the answer 3. Okay, so here's more garbage. Let's figure out what this garbage is about. So look at this. I get. Wow, I have no idea what to think about this. I have like no idea how to read this or anything. Okay, equals. Okay, let me see. Equals 0. Is a right bracket equal to 0? No, it's not. Wait a second. I know exactly what it is. Woo! I know exactly what the bug is. Oh my god! Hooray! Woo! I really like this song, so it's good. It came when a good song came. I figured it out. Alright, so this is why looking at the code has helped me, right? Even though this looks like a bunch of nonsense gibberish, right? It has to make sense because look, it is, right, I'm matching a closing bracket, opening, that's an opening bracket. Opening bracket is equal to 4. 4 is not equal to 0. Therefore, this shouldn't be this. It should be reduced. Like, it should not be in this form. It should be either true or false. In this case, false. And false selects the second thing. So it would have selected, I don't know, something in this crap over here. But the point is that I know for a fact, and not just because I remember now, but I know for a fact that I haven't defined equals for natural numbers. And that's what's causing these bugs. So let's go do that. Equals, right? And if any other bugs happen like that, maybe it's because I haven't defined stuff, right? So equals, super easy to tell if two numbers are equal, let's say x and y, right? Oh, come on, it just has to be the case if two things have to be true. X has to be greater than or equal to y, and y has to be greater or equal to x. Simple. So let's go ahead. So notice we got a star, but the star is actually equal to the number 3. Alright, let's go test it out with the next thing. Okay. It should give you 7. I think. Hopefully, if not, oh, look at that! It took a while. It took a while, but alas, we got 7, and maximum overdrive is on. So, oh wow, this is so bad, so bad. The horrible inefficiency of it. If we're not able to test a lot, then I hope you at least got to see some cool things. And yeah, we're pretty much just gonna test the interpreter now. Let's test it out with some of these nice inputs right here. Why don't we test that with this one first? Okay. Oh, we're not gonna use that one. We're gonna use this. And I'll just copy and paste this stuff into there so it's correct. Alright. Alright, so pretty much going to want to make this code real quick. Call it right star, and it equals to a list. I'm not even going to define it that long. I guess I'll just do it like that. False, true, false, null. Okay. So let's see. So 0010. And now we have interpreter. We're going to interpret that code on that tape 0010, and it should actually give us as a result. It should give us as a result this tape right here. So flip this to true, flip that to false. Let's see what happens. I like how fast that went. Really fast. 0100. Alright, let's go do a little more complicated example, and maybe two more, one or two more, and we'll see what happens. So let's view the solutions real quick just so we could see the test cases. Blah 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 blah. Let's look at a more complicated example. Not so complicated that the code will crash, but maybe something like this. This will flip all the zeros to ones. Alright? As long as you have all zeros. Okay. So I'll do all zeros, which would be that, and it just be like false, false, false. False, false, null. Okay. And now this one gonna be star, and then a bracket, and then a right symbol, and then a star, and then a closing bracket. Okay, cool. So let's go ahead and interpret that. So I get a star, star, and we're going to do that to 000, and we actually should get as a result this true, 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 which I'll just rename it 111. Alright, I'm gonna try like one more, but I'm like so sure that it'll crash and it's not gonna be pretty. But I guess we could just try it out anyways. And if it doesn't work, then I'll let you know what to say. I'll tell you the right stuff if it doesn't work. So you can be sure that this lambda calculus code is correct. Right? I'll show you how you can make sure. Let's go ahead and define this. this is code right here, and I'll just copy some of this one first. Okay, so we start off with a opening and then a star and then a right symbol and then a opening and then a right symbol and then a star and then a right symbol and then a closing bracket and then a to the right and then a closing bracket. That was pretty long code, wasn't it? I'm coding so hard right now, and we want to test out this code on this tape 001. I'll just start off by using this one. Okay, I'll go ahead and copy it into itself. Okay, and so anyways, this tape is supposed to be 0010111100. So here's the 0, here's the 0, here's the 1, here's the 1. Okay, now we can verify that it is correct. And now we're going to have the result tape here, which will be this guy. It looks pretty much the same except for this being a true and that being a false. Doesn't look very different at all. Okay. Now let's go ahead and execute. Let's go ahead and execute this. Cross the fingers right here. Woo! Look at that. Blazing fast. Blazing fast. Look at that. We get the 01001100. Wow, that's awesome. I'm so happy with the performance of my program. Let's give it just one more. And then I'm gonna head out. Okay, so we're gonna do that code on that code, and it should be this. Yep. I won't even take off the quotes. Okay. So this code, I guess I could just start off with this code. Alright, so bracket and then to the right and then a bracket and then a star and then a right and then a star and then to the right and then a star and then one more to the right and then a closing bracket and then to the right and then a closing bracket. I think that'll be it for that. Okay. Alright, cool. Okay, now the numbers, I'll just take from this list and take away two things from the front. Okay, so I have true, false, true, true, false. Wait, true, false. I have 5 things here, right? And I have 6. Let me just take out the last thing. Okay, so true, false, true, true, false. Perfect. That's the list right there. And now this one, which is the result, it really just has the last 2 elements flipped or switched. So it has false here and then true there. All right, let's do it. This will probably be the last one. So we do that code to this input, and we should get that 10101. Let's see, come on, give it to me. Now this one, maybe, yes, this one probably is way more inefficient. We could try to kind of figure out what happens by hand and try to guess what on earth my lambda calculus interpreter is going through, and maybe try to close my browser before my computer explodes. Okay, so we start off with this tape, right? And the pointer, it starts off as 0, right? Alright, so here's what we do. And by the way, we also have these instructions. Hold on. Let me just wait it out while I do this. Let's see who does it faster. My lambda calculus interpreter or me doing it by hand? Who is faster? That's 3 stars, and then there we go. That's our code. And right now the index is on this, right? The first code. The first instruction. Let me lower this tiny bit. That trumpet is getting a little louder. Okay. So here we are. We have a bracket right away. And what do we do? Let's see. We could even look it up right here. The instruction. Just to remind ourselves. Opening bracket. If the value at the current cell is 0, then we jump. Okay. Okay, I will still keep waiting on that, even though it doesn't look really hopeful. Okay, so the value, right, the pointer starts at 0, so the value is actually 1. It's non-zero. So we actually don't go to the matching bracket, but we would actually go on to the next instruction. And now we have this instruction, which is move the pointer to the right. So now it's at 1. Now we have this opening bracket, and it was actually, never mind. I read this completely wrong. Jump. We jump if the value at the current cell is 0. Jump if the value at the current cell is 0. Oh God, I hope this doesn't. Okay, good. I still have my work saved, and right here. Okay, yeah, because I'm actually thinking that, okay, yes, since it jumps right away, it seems to be not inefficient. It seems to be not a big deal for the code to run. Let's see, right? If the current, alright, actually never mind. I got so confused. It's because the pointer was 0. I got mixed with the pointer and the value. Okay, never mind. Okay. So anyways, let's keep evaluating the code. It is rightful for it to take so long because I think of what it's doing is extremely inefficient. So anyways, we're at the bracket, and since the value at the current cell is 0, we jump to the matching one. And since this one, since it's 0 here, we don't jump back. We actually keep going to the next instruction. Next instruction tells us to move the pointer up by 1. So here it is. Now the value at the cell is a 1. And now we encounter the closing bracket. Since it's a 1, we go back here. It's a 1. So we go back to matching bracket. And here it is, right? So now we go to the next instruction, and it tells us to move again the pointer to the right. And so we do. And here it is. And so now here's the opening bracket, and the value is not 0, so we don't what's it called? Jump. We actually just go to the next instruction. The next instruction tells us to flip the bit at the current pointer. So there it is. If it got flipped. Next instruction tells us to move to the right. Let me press wait here. Okay. Next instruction tells us to move it to the right. So now we do that. We change the value of the pointer to a 4. This instruction tells us to flip the bit at the pointer, so it turns into a 1. Next instruction tells us to move to the right. Oh, we go out of bounds. You know what happens when we go out of the bounds? The program pretty much ends. It tells you somewhere right here. So it ends when the commands have been considered from left to right, basically the index equaling to the length of the code, or the pointer goes out of bounds, so basically it goes less than 0 or it goes to the length of the tape. And so yeah, pretty much we are getting the correct output when doing it by hand, but who knows what the interpreter does when we run this. So I guess that's it. I think we went over a pretty good amount in this video. And now if you'd like to check if your work is totally correct and this interpreter all works and everything we've done isn't BS, you might want to head on over to Code Wars and try to solve it in Haskell. You might not know Haskell really, but you really don't need almost any syntax at all. Pretty much everything we did in lambda calculus is pretty much doable in Haskell. So maybe you want to go watch the beginning of this tutorial, learn a couple of things from it, and then maybe try out the interpreter on your own, and you'll probably be able to get it. Here we could look at it real quick. I actually don't really know that much Haskell, so I pretty much did it exactly as I did in lambda calculus, which here you could see start code index interpreter. You could see I'm pretty much doing the same things, right? I'm checking if it's right, left, blah blah blah. Flipping, I have the functions to flip the tape at the pointer, functions to jump back and forth, and well, alright. I hope you enjoyed my video, and happy lambda calculating. See you guys later.